So let's begin first with how we evaluate these different linking theory proposals using acquisition modeling. Okay, so our goal is going to be to build a modeled learner who learns close enough to how real children learn in order to tell us something informative about these linking theory proposals. So a reasonable question is, what does close enough mean exactly, right? And what I want to suggest is that it's going to be close enough to the process over here, right, which seems to have a lot going on. This is the process of acquisition involving both external information that we can observe and internal stuff happening inside the kid. And the main thing I want you to take away from this right now is that it has a lot going on, and it can be helpful when acquisition modeling to think about 5 main parts that correspond to these different pieces. So the first part is the initial state. What exactly is the child starting with in terms of knowledge or abilities, biases they might have on how to interpret the data, right? What are they starting with? And especially for our linking theory proposals, this is going to correspond to what linking knowledge they start with. Now, the data intake is about how the modeled child perceives the input, that external signal, right? So whatever information they're able to extract is their perceptual intake. And then what part of that perceptual intake is then used for learning, right? Because you may perceive quite a lot of information, but only use certain parts of it for acquisition. So the acquisitional intake is really the part we're most interested in. And so for our linking theory, if we have an utterance like the kitten was licked by a little girl, there's all kinds of information you can extract from this, but maybe we're most interested, for example, in information like if we expect a mapping already, if there was movement going on, right? Or if we don't yet expect a mapping, the distribution of those intermediate representations over the syntactic positions, right? Now, inference corresponds to how updates are made in the modeled child's internal representations, right? That's that process that then feeds into the updating of these hypotheses. Then we have the learning period, which is this whole entire process of constantly updating that developing grammar. How long does that take? How long does the child have to learn? And we often think about this in terms of time, or they have, a certain amount of time in which they accomplish this. They accomplish whatever knowledge acquisition by a particular age. In modeling, we convert this to the amount of data that they will have encountered, right? That's often one way that people go for doing the learning period. And then the target state. What does successful acquisition look like? What are we trying to hit? What knowledge is the child trying to attain in their developing grammar? And this is often assessed in terms of something we can observe. The observable behavior is used to sort of infer what that developing grammar looks like. So in the case of linking theory knowledge, right, we might have information like the little girl kissed the kitten on the stairs, and we're interested in what should we know about kiss. And maybe, because we're talking about verb classes, we want our child to know that kiss is a verb that's like pet or touch or hug, right? It's clustered together with those. And the way that we would know this is because children's interpretations or productions in context suggests that they treat kiss similar to how they treat pet and touch and hug, right? So by observing their behavior, we infer what those verb classes are in the developing grammar. So if we can define these pieces, we can make sure that we've captured the relevant parts of this acquisition process in our modeled learner, right? So that's what we're going to try to do. In fact, so let's do this for modeled learners who implement different linking theory proposals. So our goal is going to be to model the developmental trajectory of verb class knowledge from 3 to 4 to 5 years old in English, because that's the data set that we have to work with. And so let's kind of walk through the different pieces. In the initial state, we have thematic roles, right? And they yield these intermediate representations, either a fixed or a relative one. And, thematic roles are not crazy to think that kids would have in their initial state. They indicate event participant roles. They're pretty salient to very young children. So, it seems reasonable to think that our learners would have access to thematic representations, cognitively plausible. In addition, children are sensitive to the animacy of verb arguments. Like they know that little girls and kittens are animate, and they recognize that stairs are inanimate. And that seems to be information that can help them sort out verb behavior, right? And they also pay attention to the linguistic context of a verb to figure out how it behaves. We're going to call it syntactic frame. In particular, if you have a sentence like the little girl blicked the kitten on the stairs, we're going to use a very flat syntactic frame, like just literally what the argument that comes before is a noun phrase, then we have blick, the argument that comes after is a noun phrase, the kitten, and then we have a prepositional phrase on the stairs. So this syntactic frame would look something like this, right? A very flat syntactic frame, very basic, not assuming a lot of knowledge. And then we're also going to have our children capable of doing whatever statistical learning is required. They're going to have access to those abilities in their initial state. And it's not crazy to think that children have. There's lots of evidence that children are capable of doing quite good statistical learning very young. So now let's talk about the data intake, right? So the input that's going to yield this data intake comes from samples of child-directed speech from the Child's Tree Bank. And we're going to use data directed at children under the age of 3, under the age of 4, and under the age of 5. You can see this like tens of thousands of utterances between 239 and 284 individual verbs, right? Maybe a fair amount of input that these kids are hearing. And then the data intake is really going to involve the information that they're extracting. So for example, one piece of information they're extracting is that syntactic frame, which we talked about before. It might look something like this for the little girl, Blake the kitten on the stairs. However, there's actually a choice point here. We could have children either ignoring verb surface morphology, so the fact that Blick has that ed, that past tense ending, is something they could ignore, right? And so they could just encode the frame like this. Or they could pay attention to it and sort of differentiate whether it's blicked or blicking or blick in the present tense, right? And so encode the syntactic frame with that information, right? And we actually don't know what kids do, so we're going to model learners of both types. Also in the data intake are the animacy of our arguments. So again, girls and kittens are animate and stairs are inanimate. Children are going to be sensitive to this. And then we're going to have our linking information, right? So in this case, if we have an expectation of a mapping already, then this would be an example of no movement, right? Everything is kind of where we expect it to be. Versus if we don't yet expect a mapping, we're going to be having the child extract the more detailed distribution of those thematic representations with respect to syntactic positions, either under a fixed representation or under a relative representation. So, okay, now here is our basic question. Is it possible for the child to use that acquisitional intake to achieve the target knowledge and behavior of verb classes, right? That's our very basic question. What this means is that here what we're going to use is something called an ideal learner model. It's not going to be concerned with the cognitive limitations and incremental learning restrictions that children have, for example, having a fixed learning period, right? It's instead concerned with what assumptions are useful for children to have about, for example, what information they are sensitive to. And it's really good to do this before we start worrying if the assumptions are usable by children, because what if it doesn't even work out when they don't have incremental learning restrictions? It tells you that maybe this isn't the information they're using, something is not right. Hold your horses before you go doing more detailed incremental learning models. Check it out first. The basic question, is it possible to use that acquisitional intake to achieve your target knowledge or behavior? So that's what we're going to do here. And our learners are going to use a generative model of how the observable data for each verb are created. That is how they are incorporating all those different pieces of information from the data intake. And that's represented here in this lovely plate diagram. Again, it's just representing how the different information is integrated into the process of determining a verb's class. And I'm going to walk you through what that looks like in just a moment. So a verb like fall, right, that's the V right here. So each verb, right, is going to appear in a certain number of instances in the input, right? So fall is falling off, she fell down, don't fall, is London Bridge falling down, right? These are the instances. And each instance is going to appear a certain number of times, right? So maybe it's falling off appears actually like 3 times in the kid's input. So that's the data, right? That's the observable data that we have. And so based on that observable data, the child is going to figure out that each verb belongs to some class, which determines its linguistic behavior in that observable data, right? So that's your objective as a kid, to infer the verb class, which is represented up here. Now, the learner doesn't know beforehand how many classes there are or which verbs belong to which. Instead, there's a bias for classes in a power law distribution. And what this simply means is that you have a few classes that have a lot of members and most classes have very few members, right? So that's really what's going on with these variables up here, is to have that as the bias, which actually matches pretty well with what we know about how natural language items and nature in general is distributed. So it's not a crazy bias for our learners to have. Now, depending on the verb class, the observed usage down here is going to have certain characteristics, okay? And so first there are binary characteristics, such as whether the subject is animate or not, right? And so each class has a probability of preferring each option. Maybe this particular class actually kind of prefers inanimate subjects. That's just what this class does, right? And so the binary choices are always going to be the animacy of the subject, object, and oblique object. And if you have an expectation of mapping already how much that class prefers or disprefers movement, right? Then there are also multinomial characteristics, such as which syntactic frame a verb is appearing as, what is the distribution over syntactic frames. So each class has a probability of preferring each option, right? That's its preferred distribution over syntactic frames. And so the multinomial choices are always going to involve the syntactic frame, what that distribution looks like. And if there's not yet an expectation of mapping, it's also going to include the position of those intermediate thematic representations, what the distribution is of that over the syntactic positions. So now, using the observed instances of verb usage in the input, Bayesian inference is going to be used by our learner to determine a couple of different things. So 1, how many classes there are, 2, which class each verb belongs to, and 3, what the characteristics are of each class. So what's the distribution over syntactic frames, over animacy, and so on. Like, what are the characteristics of the class? And the best answer is going to be one that maximizes the probability of the observed data. That's what our learner is trying to do. And we're going to accomplish this in our modeled learners using something called Gibbs sampling. So Gibbs sampling is actually what makes this an ideal learner model, right? The inference computation that is trying to figure out the classes on the basis of this idea of incorporating information, it's accomplished using something that's neither incremental nor constrained, right? Instead, Gibbs sampling is guaranteed to converge on the optimal answer given enough time to run, and that's great because, again, we're interested in what's possible, but this is the thing that makes it an ideal learner model, is this is an idealized version of how a learner would accomplish the computation encoded here, right? This is the part that does it. If you replace this with something incremental or approximate, then you end up with not an ideal learner, right? But now we have an ideal learner. So the goal is to determine what the best answer we can get is, given this characterization of the learning problem. You use this information in this way, and this is how it generates the observed data. What's the best answer for what verbs belong to which classes and what the characteristics of those classes are? Tell me. Okay. Our basic question, right? Is it possible for the child to use that acquisitional intake to achieve our target knowledge and behavior? And we're going to basically be determining if the information provided in the modeled learner's acquisitional intake, all that animacy information, the syntactic frame information, the linking information, is it sufficient to identify verb classes the way that children seem to? So great. Now, what does this target knowledge or behavior actually look like? Okay. And the goal, again, is just to model the developmental trajectory of verb class knowledge from 3 to 4 to 5 years old in English. That's what we're going for. So what I did was a survey of 38 experimental studies on children's production and comprehension of specific verbs in English to try to find out how they behave, right? And it turns out that they have 12 different behaviors that I could find. So behaviors, when I say behaviors, I mean things like, oh, children passivize these verbs, or they don't passivize them. They use them in the ditransitive. They interpret them as subject experience, or they allow them to take non-finite to complements, right? This is what I mean by behavior. There were 12 of them. And so the verb behaviors then yield a number of verb classes at each age where verbs only belong to one class. So for example, at 3, here are some sample classes, the verbs that are known to only be passivizable versus known to only not be passivizable. Like, for example, is known to be passivizable and take a non-finite to complement, right? Like, so that's how these classes are constructed. And things change over time. So at 4, now we have different things happening. More verbs are passivizable. Like now it actually is interpreted as a psych-subject experiencer verb, right? So it's a little more complex of a class. And at 5, again, we have things sort of moving around. We have more complex behavior. For example, C is passivizable. It takes a that complementizer and also a whether or if complementizer. So, this is the kind of thing that we're looking at. We talk about classes. This is what we're trying to obtain. So when you construct classes this way, you end up with between 15 and 25 classes of between 60 and 84 verbs total between the ages of 3 and 5. That is the target state. Okay? So our evaluation is really how well did the model learner do at finding these verb classes. Okay? So the evaluation that we use is the RAND index, which ranges between 0 and 1. 0 is sad, 1 is beautiful, right? And I like it because it gives you credit for putting things together that belong together and also for keeping things apart that should be apart. So in particular, for each pair of verbs that our modeled learner put into classes, right? If for actual children, those two verbs are in the same class, and for our modeled learner, those two verbs were in the same inferred class, that's a true positive. If for our actual children, these verbs were in a different class from each other, and in our modeled child, they inferred them to be in different classes, that's a true negative. These are good things, right? Putting things together that belong together, keeping things apart that should be apart. And then if you messed it up, well, then you end up with false negatives and false positives. This happens. So the RAND index is just true positives and true negatives over all of it. Right? So it's a nicely intuitive kind of metric that gives you an answer between 0 and 1. And then you might reasonably wonder, okay, so we get this lovely answer between 0 and 1. How do we know we're actually doing better than chance, right? Like, how can you tell? So one way to determine this is to use bootstrapped confidence intervals for the RAND index, where you have randomly generated classes of random size and random verb assignment. And if the classes our modeled learner came up with are better than 99% of these, we're going to say that our modeled learner did better than chance. And if it did, worse than the bottom 1%, it did, worse than chance. We're going to focus on the ones that did better than chance. So let's remind ourselves what the different options are. So we have a couple of thematic systems. We can have a relativized system, really, or a fixed thematic system. We also have expectations about mapping. Either we don't have one yet and we're paying attention to the details of the distribution, or we have one and we're interpreting things in terms of movement. And then the syntactic frame, right? Do we pay attention to surface morphology and have multiple syntactic frames depending on what that verbal surface morphology is, or not? Do we just glump them all together? Okay, so this means we actually have 8 different modeled learners, right? Because you pick one of each, a 2 by 2 by 2, it gives you 8 possible modeled learners. And what I'm going to tell you is which ones actually worked. And the answer is that there were some for each age that performed better than chance, right? That did better than 99% of the random bootstrapped confidence interval, the randomized ones. So great, because that sure didn't have to be true. So it seems like we're on the right track. And what I want to do now is walk you through what they were. Okay, so at 3, the ones that match children's behavior involved a relative thematic representation, ignored surface morphology on the syntactic frame, but could either have linking knowledge or not. Right? At 4, we switched to having a fixed representation. Still no morphology, either have the linking knowledge or not. Or you could have no linking knowledge, pay attention to morphology, and then have either a fixed or relative representation. So it gets a little more complicated at 4. And then at 5. At 5, you have the linking knowledge, and then everything else is kind of up for grabs. You can pay attention to morphology or not. You can have a fixed or relative representation, whatever. Just have that linking knowledge. Or you could not have the linking knowledge, ignore surface morphology, and then you could have either a fixed or relative representation. So there's a lot going on with these results. And what you might reasonably wonder is, how do we interpret this with respect to our linking theory proposal? So that's what I want to do for you now. So let's take Utah. These are going to be our fixed representation. You have linking knowledge, and early maturation, in fact, would assume that both of these are present at all ages, right? So are they, right? No, right? Because at 3, that fixed representation is not there. The link could be, but not the fixed representation. It's not until 4 that you actually see the fixed representation and the link together. And then again, it's there at 5, but it's not there at 3. Right? So what this means, I think, or at least one way to interpret this, is that Utah is compatible with late maturation of this knowledge at age 4 or later. What about Utah? Right? Now, this is the relative representation. So if these are innately specified, early maturation is going to, again, assume that they're present at all ages. We're looking for both of these together, right? At all of our ages. Do we see them? Oh, there's a problem. So at 3, life is good. You have your relative representation. You have your link. Fantastic. 4, right? You have your relative representation, but then you can't have the link. You can have the link, but then you can't have the relative representation. They're not together at 4. They're back together at 5, right? So this is kind of weird. They seem to suddenly go missing together at 4, right? So this means development's complicated right? The knowledge has to be inaccessible at 4 for some reason under an early maturation story. However, a late maturation story might be compatible as well and would predict that the linking knowledge doesn't emerge till 5. So it's a relative representation with no link, a relative representation with no link, and look, there's a link in the relative representation. Great. So late maturation again for both Utah and Mutah now. What about our derived mapping variance? So the fixed one, right, would look for this knowledge to be present after the child has had sufficient language experience. So we're looking for the fixed representation always, and we go from no link to link. It's kind of what we're looking for. Do we see that? Well, we actually have the same problem again at 3. We don't have the fixed representation, right? It's just that's not there at 3 based on our results. Now, it's fine. We can have it at 4 where we have the fixed representation and either have the link or not. And certainly at 5, we have the fixed representation. We can have the link, or not, but it's not there at 3, right? The child would need to derive the fixed system knowledge as well since it's not present at age 3. What about the relative derived variant, right? So again, we have the same thing. The relative representation is supposed to be there, and we're looking to go from no link to link. What do we see? At last, right? Here's one that, doesn't have a complicated story. So here, for example, we could have a relative representation and no link at 3. We could have the relative representation and no link at 4, and then we could have the relative representation and derive that link at 5, right? Like that is one trajectory that's perfectly compatible, perfectly fine, nothing wacky going on, right? So what do we take away from this, right? I sort of walked you through that whirlwind tour. And I think one of the big things, which is very exciting, is that our linking theory proposals can now be coupled with the developmental theories, right, that have to accompany them in order to match empirical data from children, right? In particular, first takeaway is that our innate mapping approaches, Mutah and Utah, seem to require late maturation, right, of that linking knowledge. And also, takeaway 2, approaches that involve a fixed thematic system, whether it's Utah or the derived fixed representation, have to involve late maturation or derivation of the input of that fixed representation because it doesn't seem to be there at 3, right? So the question now, if knowledge matures late, how does that work? We need evidence from developmental neurobiology, I think, to understand why that knowledge would mature late. On the other hand, if knowledge is derived from the input, how does that work? It seems like we need a concrete proposal, a demonstration for how children could effectively derive the relevant linking information, right? And so that is where I want to turn now in the second part of the talk.